Welcome to the course on computer design of electrical machines. Lab lecture 22 today on the design of three-phase synchronous machine part 4 with the outline of presentation with the computer design of synchronous machines and optimization methods, design problems and references. Coming to computer design of synchronous machine. So, as studied in earlier chapter, the approach and design of electrical machines is broadly classified into two categories. Analysis method and synthesis method as given by Haroj in 1959. And by design of synchronous motor, it means dimensioning the synchronous machine for a given specification. So by design we mean synthesis, while calculating performance for a given geometry is called the analysis. So design as a synthesis uses the analysis iteratively, and analysis implies a mathematical model. I mean typically. So here is a typically a kind of different approach for typically analysis method, so which start from like a human decision, then input, performance calculation, output, and after that take a human decision either to quit or stop or to continue in a iterative manner. However, in case of synthesis method, this decision of also we give to the computer algorithm itself. So in this case, to start with the performance verification, considering suitable value of variables, then design calculation, performance calculation, compare calculated and design performance, and is performance satisfactory. If yes, total cost, then design values. If no, then adjust the value of variables, and this goes in iterative method to get the final optimum design. So now coming to main aspect in the design and optimization of electrical machine. To start with from design, we have like motor type and topology, then dimensional and material, then electromagnetics, structure, thermal and inverter and controller, and process design also. So this of course have a input and output from the typically from optimized design of the machine. To provide feasible designs and information, develop the optimization models, and in back it offers the optimal design and improvement. And the optimization of course we start with models like single or multi-objective or discrete or continuous and deterministic or robust. And then algorithm we use is classical numerical algorithm, intelligent algorithm, single or multi-objective, discrete or continuous, hybrid algorithm or others like. And similarly method strategies we adopt either surrogate model based or sequential, multi-level, multidisciplinary, space mapping and others like. So this is the typically the procedure for getting a design optimization of electrical machine. Now coming to synchronous motor design, application of computer. So comes with the scope of design starting with the specification uh, with the power rating with the kV or MVA, especially for generator, like operating voltage starting typically current for the motor and frequency 50 or 60 hertz and rated and maximum typically speed and torque, operating efficiency, duty cycle, type 3 phase or polyphase, then or single phase, then stator winding, winding turns and gauge, rotor winding turns and air gap dimension, voltage limit per winding and current limit per winding. Then of course there is 11 point insulation requirement, the winding layer insulation, insulation between winding and slot insulation, and 12 type of winding, winding type and sequence like integral, fractional, concentrated, and 13 enclosure like a frame type, and 14 type of coupling, 15 shaft design, magnetic or non-magnetic shaft, and 16 type of footing, and 17 ambient temperature and temperature rise and value within the limit. Then the 18 stamping dimensions and thickness 0.2 millimeter to 0.6 millimeter. 19 stack material like M steel, M series steel, cobalt steel, and 20 poly type, 21 flux density, designer choice on computer selection in the rotor, core and slot, or stator core and slot, and air gap. Then mode of design like computer design like synthesis approach or automatic made mode or manual design analysis method or size directed design is hybrid method. Now coming to typically the computer design with the objective typically of synthesis approach. So we have objective function which we want to max to optimize, or you can call it minimize or maximize. The objective functions for synchronous machine design could be minimize overall cost including the cost of material, labor and losses, and maximize the efficiency, power output, etc. Could be a single objective or multi-objective function. Then the constraint of synchronous machine design could be like a resistance leakage reactance, possibility flux density for that material like a saturation limit, physical dimension of machine, winding, and synchronous design is of course constraint design problem. Now coming to the variables which we have to vary to get this, the best value of objective function with the meeting the constraint requirement. The variables for synchronous machine, design could be like a main dimensions like stator, air gap and rotor. Then material choice, selection of average flux density, B average, air gap, rotor slot and core and stator slot core. Then selection of electrical loading, type of winding and turns, stator and rotor skew angle, theta linked to resistance and stack length, pole pitch ratio selection, L upon tau, current density selection, also linked to ventilation and cooling. Then the type cooling, type gas, water, superconductor and ventilation, and then 10 torque repel and many more. Now coming to synchronous motor design by analysis method. So calculation, we use this computer only for calculation, for main dimension. Data is given power, phase, frequency, synchronous speed, efficiency, power factor, specific electrical loading, magnetic loading, then winding factor, stacking factor. So from this we calculate the first the number of poles 120 F by N, then we calculate the kVA, P upon efficiency and power factor, then C0 output coefficient 11, B average AC kW into divided by 10 to power 10 to power 1000, and then calculation of D, Pm upon pi dn, bore diameter L, then we calculate L d square upon d square, then we calculate like typically tau equal to pi d upon p, and then select suitable value of n, L and n. So note, if the peripheral speed much higher than the runaway speed of 200 meter per second, then change the type of pole. The maximum flux value of peripheral speed is 175 meter per second and its nominal value is 120 meter per second. Now this is the typically the determination of main dimension for synchronous machine as a flow chart. So you input the design specification like kVA, voltage, frequency, number of poles, winding, power factor, specific loading, and calculate the number of poles if not given, like UGP 120 by N. Then find the speed in revolution per second and N upon 60, and then you go, if number of slots are given, calculate kW equal to KE, kg, kd and kp, where kp is equal to cos alpha by 2 and kd is sin m delta by 2 divided m sin beta by 2. Then find the output coefficient C0. On the other side, if number of slots are not given, assume the kW equal to 0.95 and find out the output coefficient C0 1.115 square B average AC kW into 10 power minus 3. Then find the D square L from output equation Q upon C0 and 0 NS, and is the L upon tau given? Yes, calculate tau equal to pi d upon p and L upon tau L upon pi d by p and substitute the value, and then write d in terms of L and vice versa. If no, then check whether the limit on peripheral velocity is given. If yes, use it, else assume suitable value of and terminate d from the V equal to pi dn, and substitute d square n and separate the dl and output d and L and stop. Similarly, for air gap design, that is given like a specific electrical loading, AC, short circuit ratio, ratio of air gap amp to no load and pole pitch, and typically coming to industrialization to AT equal to AC top on T, AT of equal to SCR into A, and ATG equal to 0.8, AT of BG equal to 1.5, B average, LG equal to ATG upon 800,000, BG KCG suitable. Select the proper length of air gap and DR equal to D minus 2LG and V equal to pi DR N upon 60 and N. Note that the short circuit ratio of the machine is about 0.5 to 0.7. Ratio of air gap to no load MF is constant value around 80%. Gap construction factor is always 1.1. So typically there is a flow chart for this calculation of length of air gap. To start with, input the design data, calculate the TPH, EPH upon 4.44 FKW into 5, calculate the number of poles equal to 120 F upon N, and speed in RP N upon 60, and IPH equal to kVA into 10 power 3 divided by 3 pH. 3 pH, find AT equal to 0.7, 1 IPH TPH kW upon P, and ATF equal to AT into SCR. Find the gap flux density over the pole R, BY equal to B average upon psi or B average upon L upon tau, and ATG equal to typically X% or 80% of ATA, and equate is equal to 800,000 BG kg LG, and find the LG and output LG and stop. Now coming to stator design, that is given input voltage ES, winding type, connection, stator winding factor KW, and apply phi equal to B average L into tau, And for winding type, if delta connection, EPH equal to V, else star connector, EPH equal to V upon under root 3. And if, and for connection type, if series connection, then EPH equal to EPH divided by 4.4 F pi into KW, else A equal to parallel path, so TPH equal to E into 4 F into KW, and CPH equal to 2PH and CA equal to MPH. And now number of slot selection, value of slot per pole phase. Initialization, select the value of slot per pole per phase for distribution of armature conductor. SS equal to MP into QS, ZS equal to C upon SS, and YS equal to pi D upon SS. And note, YS equal to 25 for low voltage machine, and YS equal to 40 for 6 kilovolt, and YS 60 up to 15 kilovolt. This is the flow chart for stator design with number of slots. So with the start input specification, find D and L using flow chart. Find flux per pole, B average pi D upon P, pi DL upon P. Assume or find KW equal to KD into KP, where KP equal to cos alpha by 2 and KD equal to cosine M beta by 2 and divided by M sin beta by 2. Find TPH equal to EPH divided by 4.44 F KW pi, IPH equal to KVA into 10 power 3 divided by 3 pH, and Z equal to 6 TPH or pi DL AC divided by IPH. Then find the conductor area, cross section A equal to IPH upon delta. Use given value of delta or assume it suitably. Select M equal to 3, where M is the number of the slot per pole per phase. Find the total number of slots, MPQ, where P is the number of poles and Q is the number of phases. And find the slot pitch, Y is equal to pi D upon S, and number of conductors per slot equal to Z is equal to Z upon S. Either Z odd or even, and if fractional, round Z to lower value. This must be even integer. So if it is odd, then add M equal to M plus 1, and if it is even, find Z total TPH, modify flux, then modify P average, current slot loading, then IZ into Z, and check whether the slot loading is within the permissible limit. If no, round ZS to the higher value. If yes, then stop. Now coming to magnetic circuit, data given NW, width of ventilating duct or ND, initialize ND equal to integer upon L upon NW, distribute them as duct pockets, LS equal to L minus ND into NW, L equal to 0.9 LH and N. Now coming to stator core, data given is NW, width of ventilating ducts ND, initialize phi is equal to 5 by 2, input is flux density in the stator core equal to 1 to 1. ACS equal to phi C upon BS, and DCS ECS upon Li, and DCS dash equal to 1.2 into DCS, Q equal to KVA into power factor, and loss equal to 1 minus beta into Q, and VR equal to 0.78 Q divided by beta in bracket QI plus 273 divided by 273 into 760 into 760, and note we assume the temperature rise of 25 degrees Celsius in stator is recommended for air cooled generator, and air inlet temperature 20 degrees Celsius. Now slot dimensions, data given like insert parameter, initialization, input is the reactance parameter. So D dash equal to D plus 2 SR into 10 power minus 3, YS is equal to pi D upon P, W2 equal to phi upon SS upon P into Li into 1.8, and WT maximum, YSS minus WT, IPH equal to KV into 10 power 3 divided by M into EPH. Input is current density usually 3 ampere per millimeter square. So A is equal to IPH upon sigma A, and select proper dimension of conductor. So input number of the subdivision, then the input height of the subdivision, HS, calculate the area of each conductor, modify the area of stator conductor, calculate the slot width and depth, and 17 DSS equal to DSS plus SR, and 18 alpha equal to 100 B upon WS, and 19 alpha H dash equal to alpha H 10 power minus 3, and 20 K equal to 1 plus alpha H dash power 4 n square upon 9, and 21 n. Now rotor design, the data given as insert parameter, initialization, ATR equal to 2.7 IPH TPH KW upon P, ATFL equal to 2 into AT pair, input is field winding current density 2.5 ampere per meter. Select the number of slot SR, while SR equal to odd number, go to line 11, else go to line 6, else while, so n slot equal to 0.7 SR, YSR equal to pi D upon P, F equal to 0.8 to 0.85 E upon P, LMT equal to 12 in plus 2.3 tau plus 0.24, AF equal to ATF into rho into LMT upon AF, and FCAP equal to ATF into upon AF, 17 CSR equal to C PP into N slot by P, and 18 TF equal to FC PP divided by P, and 19 CR equal to N slot by PP, and 20 TC equal to TF into CCR, 21 RF equal to F into rho into LMT upon F, 22 IF equal to F upon RF, and 23 ATR equal to IF TF. Select rotor slot and width, and 24 VIRD equal to VAR minus VAR, and 26 AAR equal to VAR by 25, and 27 AAG equal to pi D minus DR into DR by 4, and AHR equal to AR minus AG and N. So this is the flow chart for the same rotor design flow chart. So input design data, assume flux density in pole area as 1.5 to 1.7 Tesla, and leakage coefficient 1.1522. Calculate the area of pole P equal to a usual flux per pole area into leakage divided by BP, and APB equal to AP upon stacking factor. Fix the shape of the pole, whether it's circular, width of the pole WB equal to 4 upon pi AP, and LP equal to L. And if it is a rectangular, width of the pole WB AP upon LP, and LP equal to L, and output WB, LP, and AP, and stop. Now coming to slot dimensions calculation, data is inserted data with the initialized ATR equal to 0.7 IPS TPS KW upon R, ATFL equal to 2 into 8 R, input is field winding current is 2. Select the number of slot SR, while SR equal to odd number, go to line 11, else go to line 6, and Y, and slot equal, and slot plus 0.7 SR, YSR equal to pi D upon P, EF equal to 0.8, 0.85 E upon P, LMT equal to L plus 2.3 tau plus 0.24, AT equal to ATFL into rho into LMT upon EF, FC equal to ATF F, and 17 CSR FCCP and slot upon P, and TF equal to FCC by P, CRR equal to N slot by PP, TFC equal to TF upon CR, RF equal to F into LMT upon F, IF equal to F upon RF, ATR equal to IF into IF, and select the rotor slot. Then VRD minus VR, VRD 25, VRD VR minus 5D, square minus B, and AHI equal to AR. And the flow chart is for field winding design. Slot input design data is the exciter voltage specified. Now assume the exciter voltage as 125 volt for a small machine and 250 volt large machine. Then if yes, calculate the voltage across the field winding 0.85 to 1. HP known or assume, so HP equal to HP minus 20 mm, 20 mm is for spool flank height, and HP equal to is known or assume, HP equal to HP 20 in spool and flank height, 80 equal to 2.7 IPS TPS KW upon P, 80 equal to 80 into SCR, taking current density sigma F into 3 to 4 ampere per millimeter. Find the total copper area 8 frequency upon delta F. Total space for copper is 80 into sigma R, and sigma R equal space factor. Assume density of depth of the field winding DF, and the calculate the field winding LMT to LM into pi in bracket WP 0.01 dp and LMT 0.9 F, and calculate the resistance of field winding RF equal to rho LMT TF upon F, where the height of field winding AF equal to 80 LMT upon EF. Field current is IF sigma F AF, and number of winding turn TF equal to ATF and IF. Then typically go to assume the suitable winding if space height and TR is the winding height is less, increase the DF, and the winding space is more, decrease the repeat the process until the winding suitable if it HP equal to 80 into 10 divided by 10 where loss into delta of sigma the root. If loss is known, calculate the loss in the each field coil, W equal to I square RF or IF square LMT TF upon AF. Check the temperature I as equal to cooling respect to LMT HF plus dp, temperature theta equal to copper loss into CF upon S, where CF is 0.14 to 0.16 divided by 1 plus 0.1 PA. Check if theta is less than given its temperature. If no, increase the DF. Repeat. If yes, stop. Now coming to design of damper winding, data input specification. So initialization total area of damper winding per pole AD equal to 0.2 AC tau into sigma D, where tau is the pole pitch for the damper winding is 0.8 Easter slot pitch, number of damper bars equal to ND equal to pole arc upon damper pitch, and area of damper bar AD equal to AD upon number of bars, diameter of each bar equal to D upon pi 4 AD upon pi under root, and length of the each bar is L equal to 1.1 L, and output is AD. And here the typically with the start input specification, calculate the total area of damper winding pole AD equal to 0.2 AC tau divided by delta, where the T is the pole, tau is the pole pitch, pitch for damper winding 0.8 slot pitch, number of damper bar ND equal to pole arc upon damper pitch, area of damper bar equal to AD upon capital AD divided by number of bar, and diameter of each bar D equal to upon 4 AD upon pi under root of it, length of bar equal to LD equal to 1.11 LD under root AD, capital AD, small AD, ND, DD and LD stop. Now coming to synchrometer design by synthesis method. Now by synchronous motor design by synthesis method, we start with the specification constant and initial value, and then go for standard frame stamping, then design of stator winding, magnetic circuit and no load, reactance and short circuit, then performance calculation, and given for given expression go back there. So you can call it the approach to designing. Programming is generally affected by the type of size of the machine. In the case of a small standard or semi-standard machine, many of the dimensions and performance criteria imposed by international or manufacturer standard, greatly reducing the number of variables, and synthesis of the remainder of the design becomes practicable. And optimum design is generally based on the minimized production cost. Occasionally mass or marginal performance improvement are less important. So for large machine, the number of design variables is so great that optimizing may vary with the application. So the capitalized value of an optimized performance item such as subtangent reactance may outweigh the increase in price that may customer prepared to pay for it. And again, the machine may be designed as a part of extensive system, or its individual cost may be of less consequence than its performance in the system. The compressive synthesis program might take many years to develop and could be both restrictive and obsolete when completed. Analysis synthesis combination may be more practicable with the synthesis routine, dealing with easy with the adjustment of key interrelated dimension to meet a particular item in the specification, and the analysis routine copying with the many of the design calculation, balance, magnetic pole, magnetization, inertia, stresses, resistance, leakage, reactance, and losses. So in the course of a design, the coefficient may be used that are empirical function or of say two variables expressible as polynomials. Techniques are available for interrelating them so that they can be stored in a main program concerned with the required coefficient. And in all computer design, the task of forming interrelation between variables is vital. So coming to synthesis design workflow for overall design, the data is input, design specification, parameter and constraint. Next, like find the main dimension D and L, perform the design of stator, calculate the air gap and length and rotor diameter, perform the slot selection of slot, stator teeth, number of the stator conductor and winding design. And for type rotor, if silent pole, design the rotor using flowchart, else non-silent pole for the design of field winding, and design field winding using flowchart and print the result. And so here is the flowchart for the workflow of silent pole synchronous generator. Starting with the start, read the design specification like kVA, RPM, hertz, power factor, frequency, power factor, number of and width, duct, iron factor, ratio, length, pole arc, HV in thickness, ST of wedges, LP, etc. Curve fit like BS, curve losses, curve coefficient, Carter coefficient, characteristic table like B average, Q, etc. Design constraint for plug density, current density, etc. Then formulate the computer program incorporating in maximum minimum limit for rotor. Then speed, L top, pole arc, temperature rise, assume suitable value of the certain parameter and define the objective function, and run the iteration with permissible range of these variables. Then calculate the main dimension of stator core, design of stator winding core, rotor at ampere turns, open circuit characteristic calculation, load magnetization calculation, field winding design, calculation of losses, calculation of temperature and weight. Are the design constraints satisfied? No. Go to the next iteration. If yes, is the objective function achieved? No. Go to back. If yes, then print output the result and possible design variants and select the optimum design. Then synthesis design workflow for turbo generator. You start with the similar procedure, except the difference is of the sum of the design dimensions like. So now coming to optimal design of electrical machines. So design of electrical machines consists of two distinct stages: the dimension calculation stage and verification stage. And dimensioning include the choosing the material, the topology, and the calculus of all geometrical parameters starting from the machine design specification because the relationship between the machine performance indices and the geometry dimensions are related rather involved and non-linear. It is impossible to produce a set of inverse function to distinguish the latter from the former. So pi equal to as a function of fi of x, where I varies from 1 to n, where pi is the performance index from the design specification, and x is the geometrical variable and material property vector, and phi is the involved nonlinear function. So in general, there is a more than one variable vector x that satisfy pi. Also, for the some design specification, there may be no design solution except a unity power factor for synchronous motor with a certain type of electrical machine. And by classical non-optimum design, a possible x is found that satisfy most of it, not all the design specification. The optimal design select after mastering a good part of the feasible variable values, the solution that satisfy a given optimum criteria, the minimum initial cost, weight, or maximum efficiency. And after the inverses, the functions fi are not admissible to determine the vector of the geometrical variables. That's electrical magnetic stresses are chosen. Current density ampere per meter square, linear current density ampere per turns per meter, plug density B, and shear stress Newton per meter square based on the past experiences. And also some detailed slot geometry parameters such as slot opening at the air gap or slot tongue wedge thickness is given. Then using the law of electricity Maxwell equations and geometrical relation, all geometrical parameters are calculated. As the electrical magnetic stresses have been chosen arbitrarily, there is no guarantee that the geometrical variable vector x will satisfy the design specification I, and consequently the verification of permeance is mandatory as part of the design process. And the verification calculus includes the electromagnetic verification, thermal verification, and mechanical verification. So in general, to fulfill in optimum design, fulfill the performance PI, dimensioning calculus has to be redone a few times. So the geometrical dimensions is found iteratively even within the classical design. The number of iterations depends on stage chosen to change the electric magnetic stress after each verification calculation routine, and to reduce the number of iterations. A correlation between electric magnetic stress changes and geometrical parameter variation has to be established. For example, a lookup table, and however the number of iterations remains high except for a highly experienced designer who feels the way to design code. And typically here it is a classical design approach. So the stages of classical design approach are shown in adjacent figure. So dimensioning and verification calculus are computerized, but the selection of electric magnetic stresses and of initial geometry parameter is still done by the designer. If the design specifications are too restrictive, finding a solution can be either be very tedious or even impossible. So on the contrary, for low level specification machine, configuration of lower cost or a good performance may be obtained at the same cost. So here with the flow chart, design specification, choose the electrical and magnetic stresses, then go to dimensioning calculation, then calculate electromagnetic verification if yes, then go to thermal verification if yes, then go to mechanical verification if yes, then elaborate the design. If no, select the new electromagnetic stress and preliminary general format. And this is the typically optimal design fly chart starting from design specification, minimal specification of objective function, electromagnetic stresses and initial geometry variable, and then dimensioning calculus, parameter computation, objective function evaluation, electromagnetic verification, yes, thermal verification, yes, if mechanical verification, yes, if your objective function minimum, yes, then elaborate the design document. If all no, then you have to go iterative method as shown in the flow chart by adjusting the parameter. The stages of an optimum design are shown in previous slide. Optimum design specification contain in general minimum performance requirement and an objective function. Initial electromagnetic stresses and geometrical parameters are either specified by the designer or randomly generated through a dedicated routine within the specified domain. And the dimensioning and parameter calculus are done as in classical design, but additionally, objective function is also calculated. Then the electromagnetic, thermal, and mechanical verification calculation are performed, and for every performance index that is not suitable, a penalty is added to the objective function. If penalty coefficients are not high enough, then the requirement will be verified if the final design solution. Now coming to optimization method, which used for getting a synthesis approach optimum design. So synchronous motor optimization can be classified under nonlinear equality and inequality constraint optimization. In this area, there are no algorithm of iteration schemes which guarantee that a global optima, in this case is a minimum, will be found. So most of the algorithm proposed in the literature converge to the local optimum with varying degree of efficiency, although even this is not guaranteed if one starts from the iteration too far from the local optimum. So some insight is therefore usually required to find the suitable starting point for the iteration. Often past experience can serve as a good guide, and following are the three-sided optimization method along with their application used for synchronous machine design. So first is the Kring method, that is interpolation method. The optimization of synchronous motor design is usually formulated as when demonstrated interpolating Kring as value of predicted z as a function of x0 equal to I vary z 1 to n lambda I z as a function of xi. So that is for value of each sampling point, and that the value of you can call it point unique update lambda I. So in this Kring method, what called interpolation method, the Kringing method or Gaussian process regression is a method of interpolation for which the interpolated values are modeled by a Gaussian process governed by the prior covariances. And in simpler word, Kringing is one of the several methods that use a limited set of sample data points to estimate the value of variables over the continuous spectral field. And in general sense, the Kring weights are calculated such that the point near to location of interest are given more weight than those far away, and this is referred from this typically optimal design of one field machine. Typically in published in IEEE transaction of magnetics. So this is, you can see how it look like a typically designed here self-model topology of investigated machine model of stator and AC winding and rotor and DC winding, and with the specification given specification of investigated basic model with the typically poles and all the specification of the machines like. Now with the basic rotor and proposed rotor, here is a like how the parameter wise the configuration of motor with the flux barrier is investigated. The novel single flux barrier was chosen in the proposed method to decrease the XQ, while the silicon steel width with the exact pole is kept unchanged to make the LD as a constant, which leads to XD upon XQ to increase. And figures here shows the magnetic pole stress structures of a basic rotor and opposite rotor respectively, and the width of the flux barrier is 0.7 millimeter, and it's in middle of the each rotor pole. And in the next figure, the corresponding torque performance are shown, and the reluctance torque is increased from 0.088 to 0.103 Nm, and the torque ripple is decreased by 32.8%. That is one of the way how to improve. Like so, further optimization and validation using FEA, finite element analysis. So for this design process, to start, determine the objective function, constraint, and design variable. Design the experiment based on the Latin hypercube sampling. Calculate the output, perform some sampling model by finite element analysis, approximation of modeling by the Kring method, and search the optimal values of genetic algorithm. By genetic algorithm, design confirmation by FEA, satisfy target, yes and no, adjust the design variable and go to semi-iterative procedure. And here of course the objective function, if you see in this optimum design process, maximize the saliency ratio, maximize reluctance, maximize the total torque, and constraints are torque ripple should be less than like a specified value typically here 39.3%, and torque mean should be greater than 0.9292 Nm, and design variable is D varies 0.7 to 1 millimeter, and X varies from 0 to typically 1 millimeter. So here typically you can just see how it is a really analysis results of 2D finite element analysis. So good correlation between the analysis and the finite element results, and here convergence results of design is shown here. Then optimal model torque performance comparison of the operating ranges. Like so you can see the how the torque is enhanced by the shown the red curve, and how it is given in typically in case of the, let's say in tabular form, like the top ripple is reduced, as well as you can call it like in composition without, and power output is also enhanced. So coming to now method like of design of experiment, normally known as popularly known as DOE, is the process of planning experiment in a systematic way so that the data collected can be used to fit appropriate models. And prior to conducting the experiment, levels are defined for the input design variable, and full factorial design refer to a series of experiments wherein the value of the input design variables are fixed and at a predetermined levels. Like so, DOE or response surface methods are techniques which are employed for the establishment of relationship between the input and output of the system, and this relationship could be used for optimization. In case of an electrical machine, the designer is interested in the performance, say the reduction of torque ripple and cost, and the improvement of efficiency. The performances are defined as response, which are functions of independent geometrical variable like air gap, stir teeth, width, and rotor pole, except arc. Independent geometrical variable are input design variables constitute the inputs, and relationship between the responses y and the input design variable x can be established by a series of experiments. And now coming a problem formulation, for instance, in a two-level, two-factor full factorial design with independent input variable a and b, the runs are shown in the table. Out is the run, 4 runs are there, the two level with the a plus minus and b also plus minus. So the main effects are calculated a equal to y plus ya plus minus y minus yn, where ya plus and ya minus are the sum of the values of the output with the factor a at high and low level as shown in the table respectively, and n the number of turns, and the main factors for all input variables are defined similarly. Now coming to design of experiment with the typically with the two level three factors full factorial design with the a design with the abc plus minus and ab with plus minus, bc plus minus and ac plus minus, and abc with the plus minus. The algorithm for do and rs methods here define the problem input output, then statistical scanning response surface, and approximate relation between the input and output through computational efficient model, identify optimal design based on the data. Now this is typically sensitivity analysis, which is done for typically for coefficient of response curve are used to identify the effect of independent input variable on the performance. I mean, as you can see with the three-dimensional characteristics as well, typically of response coefficient with the input variable index. So coming to design of experiment with differential evaluation, so design of wound field machine, I mean for EV application as a case study. So this wound field synchronous function have several potential significant benefits and advantage of state of art of interior permanent synchronous motor and induction motor for EV application, including the reduced cost and through the removal of rare permanent material, higher system and machine efficiency through the power factor improvement, loss minimization, field control, and improved safety through direct field-oriented control using inverter fault conditions. And recently, 3 additional brushless methods of transferring power to the rotor field winding has been developed, like harmonic, inductive, and capacitive power transfer. They have been better advantage as compared to the power transfer using slip rings, exciter, and rotating, which add to the significant weight and have a higher maintenance cost. So the objective of this case study is to DOE preliminarily to identify the design space limitation, which is taken from this reference, like, and you can just see how this wound field synchronous motor used in Renault GeoEV is designed, and then the design of this EV application specification, how the WM is shown here, how the machine photograph as well as the characteristics are given here, like different characteristics are given here with the torque, continuous torque, maximum torque, and typically constant power and maximum power, and typically the specification about the weight as well as the power, maximum power of 160 kilowatt, power 60 kilowatt. Now coming to with the design of this design of this machine education, the geometric definition, this wound field synchronous motor parameter geometry is characterized by only 4D parameters: the stack length, outer stud radius, the minimum air gap, and the shaft radius, and all other features defined by 24 non-dimensional ratios of geometry, as you can see here. Typically, the shape of this geometry is of pole tip. So geometric definition: the machine pole pairs P and the number of stud slots as Z are defined so that the pole and slots are fixed, alpha P and alpha S, and from the stud geometry, the stud inner radius RSI and the stud yoke depth DSI are calculated from the two split ratio KSI and KSY of the stud outer radius RSO. So RSI equal to KSI RSI and DSI y equal to KSY into RSO multiplied 1 minus KSI divided by 1 plus KSI y. Similarly, all the dimensions of the stator and rotor are defined with the formula. So now typically the geometrical dimensions, geometry definition you can say with the different parameters shown here, and of course the flow chart for rotor pole generation, the pole type of figure is corresponding to the cases at the end of branch. So you just can see with the different logics how really the flow chart is there for calculation and design of these, typically the for geometry for particular objectives. So coming to optimization, a central composite design of experiment technique was taken to predict the maximum range of 5-dimensional variable and at the top hierarchical level to avoid the mechanical failure. So ranges are like stator outer radius from 80 to 300 millimeter, rotor outer radius 52 to 40 millimeter, and minimum air gap distance 0.5 to 1 millimeter, rotor neck thickness 4 to 44 millimeter, and rotor pole thickness 3 to 32.8 millimeter. And this is typically, you can call it how the final objective and design are there. So here torque density, which is maximized, the goodness factor, which is also maximized here, that is called torque under root losses, P losses, and a hard constraint, and this, so it's given like a torque level should be less than 0.5. So all these that are given the range here. So coming to now optimization, the optimization method used here is the parallel viscosity differential evaluation multi-objective. For each iteration, a group of designs are evaluated in parallel as they cross over the parameter of previous generation best member, and at the end of each generation, the best member are selected by the algorithm. An advantage of multi-objective differential evaluation are the implementation allow the user to set the two different types of objective and constraint on the optimization run. An objective maximize in the resulting output parameter and select the best members in the population, where the hard constraint directly eliminate the members from the population when not met, and these results containing all the possible of design are plotted on a Pareto front and the best members are chosen. Like, and typically here you can see how the optimization really goes for with the population than ripple less than Pareto front and typically with the kind of prototype. The final optimization results are shown in the figure, and each WFSM designs 7,500 total population members shown in black, and dot WFM design meeting the top ripple constraint of the less than 5% are indicated by blue dot, and the Pareto front of the trade-off designs is colored red, and the final design shown selected for prototype and experimental is yellow dot typically. So now typically it's a soft torque surface simulated red dots experiment for performance calculation. Similarly, current angles for maximum torque and field diameter is given for simulated and right torque. And here typically you can call it coming to optimization as a genetic algorithm, that is another method. So coming to as a formulation for the genetic algorithm, the genetic algorithm is a search heuristic that is inspired by the Charles Darwin theory of natural evolution, and this algorithm reflects the process of natural selection where the fitness individuals are selected for the reproduction in order to produce offspring of the next generation. And 5 phases are considered in a genetic algorithm: initial population, fitness function, selection, crossover, and mutation. You can see the process how it goes from DNA to chromosome, then population, then crossover with not open, then pure mutation after mutation, and then the process goes in the follow with the start, generate the initial population, complete the fitness, repeat, selection, crossover, mutation, complete fitness until population has converted and stop. And now typically the formulation the optimization method is used to size the generator to optimal design to by weight reduction whenever it's possible. The improved genetic algorithm is used to do so on a 2 MVA cell and pole synchronous generator. So as a steps, define the definition of design variable. Step 2 is formulation of objective function. Control objective function is a function of chromosome parameter for the task of machine. Every direction one of the objective. So Gx equal to GCUA, GUCM, GBA, GDA, GPA, GRA in kg, where all D are defined. The GCUA is the copper weight of stator coil, copper weight of excitation coil. GBA is the weight of stator yoke. GDA is the weight of stator. GRA is the weight of rotor yoke, and weight total pole weight, and G total is total weight of the machine. So next step to determine the function of efficiency of the machine as second design objective. Final efficiency is like efficiency equal to Pn upon divided by Pn plus PCA, PCM, PBFPA, PFDA, PKY and PKFI, where all parameters are defined here. PCA stator core loss, PCM excitation core loss, PFE total iron loss including lever factor, PFDA teeth loss including lever factor, KTI friction loss, PY specific surface loss of whole leg, and PKVI specific loss of this leg. Now coming to design problem. To design a 20,000 kV, 11 kV, 3000 RPM, 50 Hz, 3-phase turbo generator. The load power factor is 0.8 lagging. The main dimensions is NS equal to 3000 by synchronous speed is 3000 upon 60, that is 50 RPS. And number of poles FP equal to 2 F of 1 NS, that comes 2. Assuming the specific loading, we average 0.454 Web per meter, AC equal to 45,000 ampere conductor per meter, and winding factor KW equal to 0.955, and output coefficient from the formula 11 kW into H into 10 power 3, it comes to 60, and product DI square dq upon C0 NS, it comes 1.54 meter square. Then peripheral speed, decide the diameter considering the value of 125 meter per second. So pi d n s equal to 125, so d comes by 0.828 meter, and specific peripheral speed pi d r n r and not pi d n s. So it is used to calculate d approximately, taking a bore diameter d equal to 0.8 meter and pole pitch tau equal to pi d upon number of poles, so it comes 1.256 meter, and length then comes a product d square upon d square, that is 2.4 meter. Length of air gap length is calculated from the no load field MF turns by assuming that 75% of no load MF ampere turns are consumed by the air gap. The ampere turns equal to 0.75 no load field ampere turns, and ampere MF armature MF per pole is 8C upon tau by 2, so that comes 28,260 ampere. And assuming short circuit ratio of 0.75, so no load MF ATF 0 equal to SCR ATA, that comes 21,195 ampere. And air gap ampere turns equal to 75 into ATF, so it comes 15,896 ampere. Maximum flux density in the air gap is BG 1.5 V average, it comes 0.81 Weber per meter square, taking air gap contraction factor to be 1.15. So length of air gap is L equal to ATG upon 800,000 BGL gap, so it comes like 21.33 millimeter. And taking the length of air gap LG 20 millimeter, so diameter of rotor is DR equal to D minus 2 LG, comes 0.76 meter. Peripheral speed B equal to pi dr into NS, that comes 120 meter per second. Now coming to calculation of number of ventilating holes. So efficiency of turbo alternator is assumed 95%. Output of alternator 20,000 into power factor, so it comes 16,000, and input power output of an efficiency, it comes 16,850. The losses occurring in alternator is 850 kilowatt, and at the temperature as in stator is 28 degrees Celsius, and inlet temperature 25 degrees Celsius. So biometric height millimeter mercury is 750, H equal to 750 assume. So now calculating number of ventilating holes, so quantity of air to be let in air 0.78 losses by theta into theta plus 273 plus 761 meter per second. Putting a value, it comes 25.9 meter cube by per second. Let the velocity of air passing the duct is 24 meter per second. The a part of the total quantity of air required enters the machine via air gap rotor duct. Let this part is 25% of total, as the 75% of air enters machine via stator air duct both end. Therefore, the air entering stator 75% of 25%, so it comes 19.4 meter cube per second. Now air entering duct and air entering in the axial flux by 2, so it comes 9.7 meter per second. Total area of the holes is and air entering duct divided by air velocity comes typically 0.404 meter square, providing 270 holes each of 40 millimeter diameter, area of 3,400 centimeter square, 90 holes of 30 millimeter diameter of area is 640 centimeter square. Total area of holes is 3,400 plus 640, that comes 4,040 centimeter cube square. Now coming to stator winding design. So flux per pole pi equal to B average T into L. So putting value, it comes 1.63 Weber, and volt per phase is your 11 kV divided by root 3, that comes 6350. Run per phase is equal to EPH divided by 4.44 F5 kW. So putting a value, it comes around 18.4. So taking it 18, so 18 turns per phase. Then flux per pole increase to 1.63 and it comes to 1.6 Weber. The conductor per slot comes 2 into 15, 36, and total armature conductor is 3 into 36 is 108. Now coming to stator slot, assuming the number of slots per pole per phase 6, the total number of armature slots are S equal to 6 into 2 into 3 36. So slot per phase is 36 by 3 12. So conductor per slot is armature conductor by armature slot, so it comes 3, and stator slot pitch pi SS equal to pi d upon SS. So putting value it comes 69.8 millimeter. A slot of 69.8 millimeter for 11 kV machine is considered satisfactory. Now coming to size of the slot. So first width. So short circuit forces in turbo alternator is dependent upon the value of leakage reactance and the extent of short circuit. Thus, to reduce the short circuit forces, turbo alternator are designed to have large leakage reactance, which is obtained by deep slot. So now all 25 to 35 millimeter space is left at the top of the slot for increasing the leakage reactance, and this space is called as a reactance space, and the width of the teeth is minimum at the end of reactance space. Assuming reactance space including base is 28 millimeter. Now the diameter of the stator at the end of reactance, so d plus 2 into reactance space, so it comes totally ring value 85.6 centimeter, and slot which at this, so putting pi d into this by slots 36, that is 7.47 centimeter, and maximum flow density in teeth pt equal to 5 upon minimum teeth width into li into number of teeth, and considering the maximum flow density of the teeth will not exceed 1.9 Tesla. Putting the value, then we get the minimum teeth width pt equal to 2.47 centimeter. Permissible slot width is ws equal to ys dash minus vt comes 5 centimeter, and stator current per phase IPH, putting value it comes 1050 ampere, and let the current density in stator winding 3.2 ampere per meter. So AC stator conductor area is equal to 1050 divided by 3.23 28 millimeter square, assuming the width of conductor 25 millimeter, height of the conductor is 28 by 25 113.1 millimeter. Then if the solid conductor 25 into 13.1 millimeter is used, the eddy current loss in conductor will be excessive. So thus the conductor divided into average eddy current loss is less. So subdividing conductor in two parts. So each is the depth of 6.5 millimeter. The area of the subdivision 25 into 6.5, that is 162.5 millimeter square. The area of the conductor is equal to total 325 millimeter square. Now coming to typically for the insulation between subdivision 0.3 millimeter, conductor insulation 0.7, and coil insulation is 0.5 millimeter, 4.5 millimeter. So conductor width as a slot with conductor width is 25 millimeter, conductor insulation is 1.4 centimeter, slot liner 0.6 millimeter, coil insulation mica tube for 9 millimeter, and slackness 3 millimeter, and total slot width is now 39 millimeter, around 3.5 9 centimeter. Now coming to slot depth. So conductor height is 3 into 2 into 6.2, 39 millimeter, as you say in the typically in the figure. The conductor insulation mica, the subdivision insulation 0.9, conductor insulation 4.2, slot liner 0.3, mica tape 9 millimeter, top and bottom stretched up 2.4, reactance space is 28 millimeter, slackness 2.7, and total slot depth is around 86.5 millimeter as shown in the diagram in detail. Now coming to rotor design, the ampere MF per pole is 80 equal to 2.7 IPS TPH kW by P, so it comes to 24,367 ampere. The field MF of full load can be taken approximately twice the armature MF. So full MF is 80 equal to into this value, so 48,734 ampere, taking a current density of 2.5 ampere per meter in field winding. So the area of the conductors per pole is 280 upon delta, that is 38.98 10 to the power 3 millimeter square. So now rotor slots, the number of rotor slots you take on 23 as the number has no common factor with 36. Number of stator slot, the number of wound slot will be about 70% of rotor slot. So number of wound slot will be 0.7 into 23 16, and number of slot pitch will be by ISA pi d or upon slot. So putting value it comes 104 millimeter. Now rotor winding, we take exciter voltage 220, keeping a 40 volt for exciter in reserve. The voltage across the field winding is 180 volt. The voltage across the each field EF equal to 180 by 2, that is 90 volt, and length mean turn of field coil is LMT equal to L plus 2.3 tau per 0.24. So where tau is mean span of the coil, taking approximately 1256, the LMT comes about 7.93 meter. Now area of the each field conductor F equal to 80 to LMT upon EF. it comes 90.16 millimeter square. Number of field conductor per pole, area of conductor per pole divided by area of each conductor. So putting values, it comes for 32. The wound slots per pole is 16 by 2, that is 8. Conductor per slot 32 by 8, 54, and total field turns for TF equal to 432 by 2, that is 216. So number of coils per pole slot per pole divided by 2, 8 by 2 to 4. Turns per coil, total field turns divided by number of coils per pole, that is 216 by 454. Resistance of each field winding, that is RF into TF to LMTF on AF. Putting value, it comes 0.398 ohm, and current in field winding IF equal to F of 1 RF 95 by 0.3, they are 226 by 0.13 ampere. I have provided by field volt, so 226, and number of turns 216, so it comes 48,844.2 ampere. Now rotor slot dimensions. So sectional area of rotor conductor is 90 millimeter square. So choosing a conductor 40 millimeter wide and 2.25 millimeter deep, the insulation of slot must be designed to withstand great mechanical stress and forces which are due to slot content having a different thermal expansion coefficient. So insulation on field coil is ordered by as follows. First is 0.5 millimeter hard mica shell is provided all around the field coil. Second, over the hard mica shell, a 1.5 millimeter pluggable mica shell is provided on the field coil. Third, lastly, a steel shell of 0.6 millimeter enclose the whole field coil. And here is the rotor slot dimension. The various turns in the slot height are separated from each 0.3 millimeter press mica. The slot width is space occupied by the copper conductor 40 millimeter mica separator 1 into 0.3 millimeter, hard mica shell on conductor 3 into 1.5 millimeter, pluggable mica shell 3 into 1.5 millimeter, steel shell over the conductor 2 into 0.6, that is 1.2 millimeter, mica strip on the slot 2 into 1.3, 2.6, and slackness 0.9 millimeter, and total slot width is 51 millimeter, that is 5.1 centimeter. Now coming to rotor slot depth, the copper conductor 54 into 2.5, that is 121.5 millimeter, mica separated 15.9 millimeter, wet 25 millimeter, flexible mica or 4.5, hard mica 1.5, steel shell 1.2, mica top 1.3, strip steel plate 2 millimeter, copper strip to the weight 2.5 millimeter, slackness 1.9 millimeter, total 171.3 millimeter, that is 17.3 centimeter. Now these are the references which are used to develop this material, and thank you very much.